So now we are going to move on to another part. That's actually the last one. After this, we are done. So I'm going to start today, and then I'll finish next week. It's called language models. So now it's a few years ago, when you said language model, it wasn't a buzzword. So, just a section like any other. And now, of course, when you say language model, everybody thinks of LLMs and ChatGPT and, all of these models that are very popular today. So I will contrast it. I will explain also the differences. So what is the difference between a large language model and a language model in the classical sense? It's very important to know, this is kind of the history, right? So before the large language models, how did the language models appear? So I'm going to give you all that was done around these language models in such a way that then, for those of you who are interested, you can go to the LLM course and then learn the large language models with the history in mind of what has been done before. And again, with the idea that a large language model, if you think of it, is just a search engine. It's just a better search engine that actually can understand the semantics of the language via the embedding in the vector space. All right, so I'm going to start right away with a cool toy that you might know from theoretical computer science. Who has ever seen this thing? I see a lot of nodding. So yes, you've seen these things. So it's known as a finite state automaton, and it's used in the context of languages, which shouldn't be surprising because we are talking about language models, right? But with language here, we don't mean just English or German or human spoken language. We just mean language in the theoretical computer science meaning, right? So in a language, in the computer science meaning, is just a set of strings. Right? So the string, the set of all string has something that's called the monoid structure. Monoid just means that you can concatenate two strings. You have the empty string. When you concatenate it, it doesn't change anything. So that's called, and it's associative, and that's called the monoid structure. And so when you have defined this, the set of all strings, then you can define a subset of this set of all strings, and such a subset is called a language. And when you have a language, the first thing you want to do as an interesting problem in computer science is you want to identify the strings that belong to that language or not. So if I give you a string, you want a way to tell me, yes, that string is in the language, or no, that string is not in the language. It has direct applications because, in fact, when you write a Python program or you have an XML file or a JSON file and you try to parse it in an editor, you're doing exactly that. Right? The computer is looking at your text file, which is a string, and it's trying to tell you yes or no, is it accepted or not, right? Does it parse, does it not parse? If it doesn't parse, you're going to get some errors. If it parses, then you get the syntax highlighting. Suddenly, everything is enhanced with colors and so on. And so these automata, as you might remember, they are here to recognize the strings that belong to certain languages, some languages, not all of them, but there are certain languages that can be recognized with that kind of things. Which, if I'm correct, is called a regular language. That was so long ago for me. So the way it works is that we have these nodes that are connected in this way with edges, and the edges have labels that are called transitions. And what you have on the labels, these are the letters of your language, A, B in that case, so this is your alphabet. And then a word is just a sequence, a finite sequence of such letters. And so the interpretation of that graph is that whenever you have an edge going from one node to another node and with a specific label, it's a transition from a state to another state, depending on the letter that you see. For example, if you look at the transition table on the right, if you are in state number 1 and you see an A, or you consume an A, then you go to state number 5, and that you see with the arrow that goes from 1 to 5 labeled with A. And B would lead you to state 2, which you see with the edge from 1 to 2 with B, all right? Is it all good? You've seen that, right? So this is just to refresh a little bit. And so the way it works is that you just have your string that you want to test, and you just put yourself at the start, right? It's like a video game. And you start right here, and then you consume one by one the letters, and you follow the transition table to go where it tells you to go, B, A, 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 A. And now I have this little rectangle in here. It's just where I accept, right? If I end up in here, then it means that I'm going to accept the word as part of the language, which is what's happening right here. In fact, it's going to accept it with any number of further letters A, okay? You know regular expressions, right? What would be the regular expression for the language that this accepts? Yes? BAA A star, yes, or BAA plus, which is equivalent, right? So BAA A star, absolutely. So this is also connected to regular expressions. Of course, there's many more languages. You also have more powerful ways like context-free grammars that are even more powerful than that, and then gets even more and more complicated. And of course, the human languages, these are the toughest, right, to get. This is where the LLMs actually were super useful. This one gets rejected. BA goes to the sink. This is called the sink, right? It's just the trash can. Whatever follows, you're just there and that's over. All right? So formally, you do that with a bunch of letters and delta for the transition, it's a function, and big sigma for the alphabet, F for the state of finite states, and so on, right? But I'm not going to annoy you. There's sufficient notation elsewhere, so I'm going to stick to the drawings for that. Speaking of notations, that's actually the one we are going to use. So again, a language is a set of strings. So I'm going to call my set of string D in a curved letter. It's a set of documents, right? A string, I can call it a document, right? A document that I have on the internet is technically a string, right? And I can ask myself, do I accept it or not? The letters here, B, A, and so on, if I map it to information retrieval, these are in fact the words. So the words that belong to documents correspond in the regular language terminology to letters in strings, right? So it requires a bit of a jump, cognitive jump, that you really need to consider the terms, the words, as letters, as in terms of the regular language. So I have documents that are sequences of words. And so what I'm going to have for my language model is a probability distribution. More precisely, my documents are random variables. That shouldn't be new, right? We've been doing that for 2 weeks, that we had random variables that are documents. And so I associate every document that can be a value of my random variable to a number. And if I sum the probability over all documents, I get 1. And I prefer this notation. It's the same, right? You can use this, the one or the other notation, and I use that notation more for the probabilistic retrieval. All right, so if I sum over all documents, small d, then the probabilities sum up to 1. So again, I have a language plus a probability distribution over that language. Is that clear for everybody? Right? All right. And so again, if it helps, whenever you see these formulas with the probabilities of documents and so on, think of the little elves, right? The elementary events, septillions of them, and every one of them is associated with the document, query, or everything we need. Now, the first cool thing that we can do with this is that we can repurpose this finite state automaton as a generator. It's like generative AI, right, with ChatGPT. Not only can you identify or understand things, you can also generate stuff. So I'm not going to call this ChatGPT because it's nowhere like it, but in fact, we can use that in order to generate documents. Imagine that A and B, which are letters here, these would be words, like information, retrieval, ETH, and so on. So how can we turn that into a generator? Well, I can add some probabilities for the state transition. If I add a probability, and then I just toss a coin every time. I toss a coin, maybe B, maybe A, with probability 1/2 every time, or I use dice if you prefer. And then, so for example, here, with probability of 1/2, I get B. With the probability of 1/2, I get A. With the probability of 1/2, I get A. And then, bam. And so here, the probability that I generate this number, ignoring whether I accept it or not, is 1/64. Right? So it's 1/2 for B, 1/2 for A, 1/2 for A, 1/2 for A, And then 1/4, that's the probability of stopping every time, right? So it's independent, right? So when you arrive there, you decide, do I stop, do I not stop? And if you don't stop, then you toss a coin for A or B, right? And then you check again, do you stop, do you not stop? Then you toss a coin again, right? So here we get a probability of 1/64. Then of course, if you consider only the words you accept, you need to renormalize with the probability of the language, the entire language set. Who is with me? Right? It's quite simple, really. I just invert this and I just use it to generate instead of consuming the words. So now it's pretty cool, right? That we can start generating documents in this way. Now, if I do a little bit of math, we are in fact in known territory. Because if you think of it, a string is a sequence of letters. And since I said here a string is a document and a letter is a word, a document is a sequence of words. We've already seen documents as sequences of words. That is the list of word model, right? We can have sets of words, bags of words, lists of words. So when we are looking at documents in this way, as sequences of words, we are looking at the list of words model, right? All right, and in this semester, we've emphasized more sets of words for Boolean retrieval, bags of words for vector space model, sets of words for probabilities. But now we are going to go into the list of words model, which is pretty cool. We've already also seen the list of words for phrase search, right? When you have the byword indices and so on, phrase search, that's also a list of words model. But anyway, I have a document. The uppercase D is a random variable that takes its values into this set of documents, which again is a monoid, T star. And then I can have another random variable that is its length, right? It's just a function of the document. If I have a document, I can take its length. And you probably agree that that gives me a random variable, which is the length of the document, which also has a probability distribution over the length. So I'm going to call it LD, right? The document length. I could have just called it L, right? It would have mattered, but I just put it LD for making clear that it's the length of some documents. And so now, what we are going to do is that we take documents, we take one document, and we can use that document in order to generate other documents. And now, again, it starts sounding like ChatGPT, right? And the way we do that, if you think of that, how can we get a generator like this, so this finite state automaton? If you come back to here, what we need is the weights. We need to have some structure, and we need to know the weights every time, the weights that I'm going to be associating to the letters. Now, how can we get these weights? So you probably start having the intuitions by looking at the documents, right? If there are words that appear a lot in the documents, then there will be a higher probability, they will have a higher probability of being generated. And if you have words that are a bit rarer in the document that you're looking at, the probability that they get generated is lower, right? That makes sense, right? We're going to have a higher probability of generating the frequent words. And so that's exactly what we are going to be doing. We take a document, we analyze it statistically, and build out of that document some generator of words. And so that generator of words, what you have to imagine is that it always comes down to a probability distribution over the documents. Once you have a generator of documents, that gives you the probability distribution. It's the probability that this specific generator will generate that specific document. Right? So now, if we take our list of words model, and we use, don't be scared, I'll explain, and in fact, you will see it's pretty easy. I'm going to use the chain rule. Remember that the chain rule gives me the probability of some conjunction of events, A, B, C, D, and so on. So the probability of A, B, C, D is the probability of A times the probability of B knowing A times the probability of C knowing A and B times the probability of D knowing A, B, and C, right? That is my chain rule. Everybody with me? Right? So that's the chain rule. So now I'm doing exactly this. I'm going to look at the probability of generating documents D1, D2, D3. D1, D2, D3 can be anything, right? These are just lowercase, so these are mathematical variables. So here I could put information retrieval system, right? So D1 is information, D2 is retrieval, D3 is system. Word of warning, the subscript here, that's not the same as in the previous week. The subscript here is just a position. Position 1, position 2, position 3 in my list of words. That's not like in the probabilistic information retrieval where we had a vector. So just remember that. Not the same notation. So the first word, the second word, and the third word. And now I'm asking the question, what is the probability that this generator that I built is going to generate exactly that document? The probability that I'm generating, so D is equal to exactly that, specifically, and it stops here. So when I look at that document, I'm just going to decompose it into multiple things. How do I obtain that document? First, do you agree that the first thing that should happen to generate that document, it has a length of 3, is that I have to generate at least one word, right? Because if I don't generate anything, I'm not getting that document. So my first event, and I will have a conjunction of them, is that the length of the document, this random variable, must be at least 1. But that's not enough, right? Because otherwise I would generate any document that has a length of at least 1. So the second thing that I must have is that my first word must be D1. Information, for example. Conditions on the length of at least 1, because that's the chain rule, right? Probability of AB is the probability of A times the probability of B knowing A. So these first two here, probability of LD greater than 1 times the probability of D1s equals D1s, information. If you multiply these two, this gives you the probability of the conjunction. This is the probability of this and this. Who agrees with that? It's the chain rule, right? So at that point, when I'm here, I have the probability of having a document of length at least 1 and of having information, D1, as my first word. But that's not enough, right? Because right now I'm only here. What should happen next to get this document here? What should happen next is that there's one more word. So now I'm going to throw in one more condition. It's that the length must be at least 2. Conditioned on the fact that it was already at least 1 and the first word was D1. That's again my chain rule. So now if I take the conjunction of all of that, it's this and this and this, right? So it's the probability that the length is at least 1 and the first one is D1 and it's at least 2. And then of course I can, if you realize that this implies that, then you can drop that. So at that point, when I'm done with the first 3 factors up to here, I have the probability that the length is at least 2 and the first word is D1. What happens next? The next word is D2. So now I multiply with the probability that the next word is D2, conditioned on what came previously, conditioned on the fact that the length was at least 2 and D1 is D1. That's again the chain rule. At that point, I have a length of at least 2 and D1, D2. And then I continue. The next thing that must happen is that the length is at least 3, condition of everything that came before. Then, knowing it's at least 3, the third word must be D3, conditions and all of that. And it must stop. Now, my stopping condition is that the probability is equal to 3. Conditions on previous, because of the chain rule. Who gets that formula? Right? So in other words, if I look at the probability of obtaining exactly that document as the conjunction of length at least 1, first document is D1, length at least 2, second word, sorry, not document, second word is D2, length at least 3, third word is D3, length exactly 3, the conjunction of all of that, that is equivalent to that, and I'm writing it as the chain rule. That's what I'm doing here, just the chain rule. Now, if I look closer, there are similarities in there. Look at all these probabilities where I have the probability that the length is at least n plus 1, given that it was n, right? I'm adding one word. And look at the probability of the length being exactly n, knowing that it was at least n. If you think of it, that's the probability of stopping versus the probability of continuing, right? And so here we can give them some constants, and we can decide that these are constants. So I have p stop, P stop is the probability of stopping. It's just a number, 1/2, 1/4, whatever. And we just say, okay, that last probability here is P stop. And the other one is 1 minus P stop. It's just the probability of stopping or continuing, right? Generally, that must not be, it doesn't need to be a constant, right? That could depend or it could vary and so on. But we are just in our model, for the purpose of our model, we are going to assume that there is a P stop such that this is P stop and 1 minus P stop, okay? And there is a second, so the first assumption, P stop, 1 minus P stop. And I'm going to make a second assumption, which can be argued is a limitation of these older languages. We are going to assume that we don't have unlimited memory, because I wrote that chain rule with just 3 documents, right? D1, D2, D3. But it can go on and on and on and on and on with millions of letters, right? You can have huge documents. And so if you write that chain rule, you're going to have the probability of generating the millionth word given each one of the 999,999 other words. That is a huge list. That is a lot of memory that you need to build a system like that. And that was a few decades ago, right? We didn't have so much computing power and so on. So we introduced a simplifying assumptions, which is called the Markov rule. We assume that, in fact, we only remember a window of words. The last, what did I call it? The last n words we remember. So it means that the probability of the next word being what it is, depending on everything, is the same as its probability knowing only the previous n words, right? So we have a memory, a limited memory. We only look at the previous n words. And that is some parameter of the system. We look at the special case of not having any memory at all. We'll see, it's called the unigram model, which behaves a bit differently from the ones that do have a memory, where you have 1, 2, 3 or more words before, right? So look at that formula. The only thing it's telling us is we forget everything that's too long ago in the past, right? The probability of the next word only depends on the previous n terms. That is a big difference with the large language models like ChatGPT, because in large language models, you have a much better reach. When you look at a word, it reaches much farther in terms of connections to the other words. It even goes to the future in ChatGPT, when that's the attention mechanism. Here, we only go to the past. We link a word to what was before. But in LLMs, you go both sides. You have this attention mechanism that connects the word in its context to everything that's happening around. So now it looks a bit primitive, right, compared to LLMs, but this is historically the first way that we analyzed and generated some language. So we look at the previous n terms. And so now if I do that, let me have a window, a memory of 2 words. I only remember the previous 2 words. If I want the probability of generating exactly documents D1, D2, D3, D4, Polyban is unexpectedly working, for example, 4 words, then you get that. It's my chain rule, exactly the chain rule, but now I put this 1 minus P stop. So probability of D1, D2, D3, D4 is the probability I don't stop times the probability of getting D1, times the probability I still don't stop, times the probability of getting D2, given that I had D1, times I still don't stop, times the probability I get D3 conditioned on D1 and D2, times I still don't stop, and now the probability I get D4 based on D2 and D3, not D1, limited memory. I only have the memory of the previous 2 words, and then P stop. Who agrees with that formula? Right? It's just a chain rule using the assumptions. P stop and 1 minus P stop are constants, and we only have a memory of 2 in that case. It's a parameter. Now, just looking at my watch, if I have to let you go, no, I'm going to let you go. Forget that I showed that, because that's going to start a whole new thing, and then in 5 minutes, I'm just going to lose you. So we stop over this one, the chain rule, with the Markov rule with a memory of 2, and P stop, 1 minus P stop. So thank you. everybody for attending this lecture. Enjoy the exercise session, the mystery game. Do we have a winner already? Okay, so the results are going to be checked. So I hope you enjoy all of this. So enjoy the exercises. I'll see you next week at 10 a.m. as always for the continuation of this. In the last week of the semester, we are just going to enjoy, have a quiz with everybody and a wrap up of the semester. So the material should stop next week. Thank you very much. Goodbye. See you next week. And thank you, Georges, for moderating.
A quick note, actually, the mystery game will be released later today.
Oh, it's not.
So yeah, we haven't released it yet. Okay, so it will be released today.
Okay, yeah, that's great.